So, hello, I'm Petros. First of all, my apologies because I was in California until yesterday, so I'm jet lagged as fuck, and if I'm not entirely coherent, that's why. Other than that, I'm the SaaS reliability manager for Confluent here in Europe, and really our bread and butter is Kafka, but I'm part of the team that actually provides Kafka and the rest of the ecosystem as a service. So we run across multiple clouds, and we take care of our stack. We don't so much interact with the on-prem side of things. So this talk really covers how we run Kubernetes and how we run our products on top of it on the cloud. So other than that, also if you want to talk more about Kafka, we do run separate talks, and you can probably grab the URL off me later on. So why Kubernetes? For us, Kubernetes is less about it being an awesome cluster manager and more about actually getting us a standardized API across cloud providers. Really, our main cost is networking. If you're putting data in or out of Kafka, really the main thing that we're paying when you're running on us is network costs. So largely, we need to be close to you in the particular cloud provider you're in. Ideally, we want to be as tightly VPC peered with you or whatever networking model the cloud providers. But both latency and costs of peering is very important for us. So since our clients run on AWS, they run on Google, they run on Azure, we're talking with people who want to run on Huawei or Alibaba. That means we actually have to run on practically every single cloud provider on the planet, and we need an easy way to do it. So Kubernetes gives us that. Largely, it means we can program against a single set of APIs and programming models when running our software. And it allows us to go to a new cloud relatively soon. While it doesn't hide all of the cloud differences, it hides the vast majority of them. Also, I've genuinely never enjoyed my job quite as much as when working with Kubernetes. I've worked with Mesos, I've worked with Yarn. I actually hate both of them, so yay for Kubernetes. However, 1.6 was terrible to run with. Like, actually keeping it up and running was genuinely painful. If it went down, good luck bringing it back up. So I'm kind of glad I didn't have to work with the stack a lot at that stage. 1.7 was actually kind of a happy place for my team. Mostly the cluster stayed up and running by itself. We had the occasional issues, but by and large, it didn't generate a lot of problems for our teams. 1.8, that was incredibly painful. Basically, at this point, we had on-call alerts on occasion 7 or 8 times a night, just because of the API masters blowing up in wonderful ways. Either memory leaks or grabbing the lock for some sort of process and not releasing it and silently dying, or all sorts of wonderful problems. I hated 1.8. 1.7 actually is the first time Kubernetes has felt like production ready for us. I know many people will bash me for saying that, but 1.7 finally didn't cause us any problems in terms of running it. After upgrading to it, our incidents went basically from probably 7 or 8 master crashes a day down to nearly 0. And 1.10 onwards, we're still happy, we're still upgrading with upstream. But after what happened with 1.8, we're actually quite careful about validating before we move to the next version. So how large is our footprint? You might notice we run a lot of Kubernetes clusters. Mostly for us, actually running extra Kubernetes clusters is relatively cheap, meaning that our storage costs and our network costs dominate our cost model so far, that running lots of them is not a problem. We add 3 to 5 clusters a week without a problem. We've gotten quite good at running a lot of them by now. And we're mostly on AWS, but we also do run a little on GCP, and we'll be offering Azure pretty soon. We do segregate per account. That's the typical thing you'd expect. And soon enough, we'll likely be doing basically an account per client on AWS specifically. Because one of our major problems with scaling Kubernetes is actually just Kubernetes trying to roll too many load balancers or making too many requests to AWS. The number of times AWS has rate limited or outright blocked us for its ELB APIs, which are global per account, that happens quite often. It's quite unpleasant. Other than that, we also mostly run symmetrically, meaning that since the majority of our workloads are Kafka, nearly all of our instances are just R4X large. We're considering moving down the line, but AWS and a lot of other cloud providers do this annoying thing where they lock the ratio of CPU to disk to memory, kind of like linearly across a large set of instance classes. So actually, R4X large is a bit of a sweet spot for us, and we don't see much of a reason to move out, since most of our software scales very linearly. We actually started trying to automate Kubernetes using Python. We discovered pretty early on that was a pretty big mistake, especially trying to deal with templating YAML primarily, or even with the Kubernetes API within Python, just generated a very large number of interesting problems. There's the joke that 80% of errors have to do with not having a type system. That's definitely the case for us. So pretty soon we moved over to Golang, and we've kind of like been there ever since. We tend to use operators, even though we have one operator right now that takes care of all of our products. We're breaking it up down the line. And mostly, we find that using protobuf, gRPC, Kubernetes, and Kafka gives us a kind of like an end-to-end type system, whether we're going asynchronously over Kafka using basically a binary protobuf, or we're going over gRPC for more synchronous communications. Overall, it maintains a nicely typed and coupled system all the way down. So how do we monitor things? Datadog, mostly. We use that a lot. Yeah, we're not entirely happy with it. I'm not going to lie about that. But it does get the startup up and running with like most of the things you would need. Some of the main problems we have is actually on occasion it even leaks data between different accounts for us. Like sometimes I'll genuinely be on the production account and end up seeing interesting data from development in the production account. And also if you're trying to actually scale to very large amounts of data, it outright crashes my Chrome randomly. So probably we'll be moving off that onto our own stack sooner or later. Other than that, pretty typical ELK stack using hosted on AWS, which, to be fair, us running on AWS on a random node is kind of getting awkward since they provide a competing product right now as well, but that's the place a lot of people find themselves in sooner or later. And all of that feeds PagerDuty. I'm sure PagerDuty is the bane of your lives for many of you, but it's a pretty good product overall. Another thing we're doing right now is we're growing our own metric stack. So basically, Datadog kind of works if you're trying to monitor your own stack. It really doesn't work if you need to offer metrics to your own clients. So we've built our own Prometheus scraper, and we generally offer the clients to consume their own metrics data over Kafka, basically, and just feed it to their own Datadog account, their own outlier account, or whatever else they need to do. So slowly, we're ending up building our own metric stack just because we need to provide good data to our clients. So how do we actually schedule over so many Kubernetes clusters? So the current Kubernetes federation layer is kind of like YOLO style. Basically, if you want to use it, best of luck in surviving it. At least that was our discovery. So we've mostly built a fairly light scheduler on top of it. For the most part, the gRPC request goes into our scheduler. The scheduler gets a few requirements like how large do you want your Kafka cluster to be, what location do you want it to be, do you have any special zookeeper requirements, do you want it to be HA, so on. Goes over Kafka, writes a number of messages basically into Kafka. That might result in additional requests like my API keys might be generated, Kafka scheduling requests might be generated, zookeeper requests might be generated. That message goes over Kafka to something we call the sync service. Each sync service generally knows which cluster basically it's running on and just goes ahead and picks up the messages for it. Writes it to a custom server resource on Kubernetes, which we call a PSC, physical stateful cluster. And then our operator actually goes ahead and actions it. The operator is really what actually does most of the work for us. All the other things just generate PSCs for it to action. So a scheduler gets quite complicated, and actually we've gotten this wrong quite a few times while trying to build a scheduler, so we're even rewriting this. But generally speaking, the scheduler is split into two parts. The main scheduling logic and the event loops and so on, and the number of plugins that actually generate the actual plan for our product. So depending on what product, whether you're in, say, Kafka Connect or Kafka itself, the scheduler knows there's a plugin. It'll go over to that plugin and file a request saying, hey, please design me a cluster meeting these requirements for the request. That'll generally give it things like pod configuration, config files. It might tell it, hey, you have these additional dependencies. Go over to the Zookeeper plugin and also request some additional information. But between the two of them, eventually they'll figure out the right set of messages to enqueue in Kafka and send them off. This is vaguely kind of like the request. It is kind of a loop because quite often a Kafka request, a request for a Kafka cluster will result in a request for a Zookeeper cluster, will result in a request for a Kafka API cluster, will result in a set of API keys being generated. So depending on what you've requested and how much of it already exists in the particular region, there's a number of requests that will go back and forth. So, operator, what does it actually do? For us, that's the bit that actually implements anything, meaning that it doesn't actually talk very much to the outside world. It pretty much only talks to the Kubernetes API, and it actually doesn't have any of the logic for it to know what to do. It doesn't know how to create SSL certificates. It doesn't know how to create API keys. It expects mostly a fairly complete definition of what it's supposed to do to be given to it on the PSC. And it really only cares about the particular Kubernetes cluster it runs on and the particular cloud it's trying to run on. The main reason why it's actually our simplest code base, it's also because it's the code base that can actually delete all our ABS disks at one go if it decides to go crazy. So it's probably our most heavily tested code base. One of the things we embraced early on, especially since Kubernetes 1.6 blew up in interesting ways, was that we actually didn't want one very large Kubernetes cluster. Even though we trust Kubernetes a lot more, we like the fact that we run a lot of them. Any one of them blowing up usually results in a very small blast radius for us, limited to a very strict subset of clients. And also, we can separate Kubernetes clients by the size of client and the criticality of client, basically the amount of traffic they're putting through them and the disruption it'll cause. So that's the good part. The bad part is on occasion if our scheduler does something interesting, and especially if there's something like a timing bug or something like that, it can generate lots of little problems per Kubernetes cluster. So, which might mean that if you have 80 Kubernetes clusters in production, each one of them might actually generate a completely different set of problems since it's all asynchronous. And that you can't usually just write a script and expect it to consolidate across everything, especially if you don't fully understand the timing bug that's occurred there. So that can be a little bit painful on occasion. On the bright side, overall, we feel that it's better this way than the other way around, but I'm not going to say it doesn't have its problems. So, also, why did we go for a relatively complicated scheduler architecture? We don't just have Kafka. If we just had Kafka largely, we might have gone just throw it on EC2 instances or compute instances or so on. We have KSQL, we have Connect, we have Streams, we have C3. All of them tend to have different requirements, especially the products like Streams and KSQL, which are essentially fancy Lambda executors in a lot of ways. Those need to be very flexible in their scheduling, and Kubernetes' API largely will let us support them as products in the future. And something that a lot of people didn't realize when we started building basically a SaaS versus just a software product we sell to people, 70% of the work we've done has been completely unrelated with the thing we actually sell. We've had to do billing integrations, security integrations, monitoring, alerting, RBACs, and all of them tend to be different per country, especially when you have legal guarantees where you have to give people money back if you basically mess up your infrastructure. So all of these SREs have actually been getting quite busy with talking to the legal department for nearly like half of their time for some of our quarters. It's a lot of work. It all has technical implications on average, and if you get any of it wrong, it tends to hurt the business quite badly. So mostly I've enjoyed it. Some bits of it I've really wished I didn't have to do and someone else could do it, but that's not how it works usually. So, and that's about it, basically. If you have any questions, I'm more than happy to answer them.